We're just bombarded with numbers every single day, right? In the news, at work, in ads, everywhere. But how often do we actually stop and ask, wait, what is this number really telling me? Well, in this explainer, we're going to give you a toolkit, a way to see through the spin, spot the traps, and become a much, much smarter consumer of data.
So let's kick things off with a little cautionary tale. It perfectly captures the danger we're all in when we put way too much faith in a single, simple number.
This quote is kind of morbidly funny, but it just hits the nail on the head, doesn't it? An average depth of 3 feet? That sounds totally safe, but that one little number completely hides the reality of, say, a 6-foot deep channel right in the middle. So, yeah, the average was technically correct, but it was also completely useless. Dangerous, even. And this classic mistake, it actually has a name: the flaw of averages. It's this simple but really dangerous idea that a plan based on an average is going to work out fine. It's like designing a car for the average driver. It wouldn't fit almost anyone perfectly. The average just papers over all the variation, and in the real world, variation is what gets you.
And believe me, this isn't just some hypothetical problem. Back in 1994, Orange County, California went bankrupt because their investment plans were all based on average interest rates. They completely ignored the massive risk of an extreme event. And then, a few years later, the city of Grand Forks was devastated. The river crested just a little bit above the forecast average, and it overwhelmed the defenses that were built for that one single misleading number.
Okay, so if the average can be so misleading, what's a better way to get at the truth? Well, that brings us to our very first tool: understanding the crucial difference between the average and what is actually typical. All right, on the left, you've got the mean. That's what we all call the average. Think of it like a seesaw. One really, really heavy person sitting on one end can just throw the whole thing way off balance. But on the right, we have the median. This is more like finding the person standing in the exact middle of a line. It doesn't matter how heavy the folks at the ends are, that middle person's position just doesn't change. And just look at how this plays out with these 5 incomes. The person in the middle, the median, makes a totally reasonable $30,000. But because one person in the group is a millionaire, the mean, the average, just skyrockets to over $218,000. So which number do you think really describes this group? Yeah, it's pretty clear.
This lopsided shape has a technical name. It's called a right-skewed distribution. But honestly, just think of it like a playground slide. Most of the data points are all clustered down at the bottom, but you've got a few high flyers way, way up at the top. And that average gets pulled way up by those few at the top, making it seem like everyone is higher up than they actually are.
So here's a pro tip for you. Anytime you see data on stuff like household income or real estate prices or even hospital wait times, your spidey senses should start tingling. These are classic examples of skewed data where you should immediately ask, okay, that's the average, but what's the median? Trust me, it'll almost always give you a much more realistic picture of what's going on.
Okay, so we've learned to be a little wary of the average. But what happens when we're given a whole bunch of summary numbers, not just the average, and they all look pretty much identical? This is where we get into a much more subtle and, frankly, a much more dangerous trap. So back in 1973, a statistician named Francis Anscombe came up with this brilliant little puzzle. He presented 4 different sets of data that, on the surface, looked exactly the same. I mean, just look at this slide. They have the same mean, the same variance, even the exact same correlation and regression line. They're basically numerical twins. But as we're about to see, looks can be very, very deceiving. So based on the numbers alone, you'd have to conclude these data sets are all telling the exact same story. But are they really?
Let's pull back the curtain and actually look at the graphs. So here's the first data set. It's a classic, right? A nice, well-behaved set of points, all clustering neatly around an upward sloping line. This is exactly what the summary statistics promised. No surprises here. But then we get to the second data set, and whoa, everything changes. This is not a line at all. It's a perfect, graceful curve. A beautiful, clear relationship that those summary statistics were completely blind to. They tried to force a straight line onto a curve, and they just failed spectacularly.
Okay, next up, data set 3. Now here we have an almost perfect straight line, but it's completely hijacked by one single pesky outlier. That one point, just sitting way off by itself, is like a little black hole. It's bending all the summary numbers toward it and just distorting the truth of all the other data points. And finally, the most shocking one of all,
In dataset 4, there is absolutely no relationship between the variables, except for one powerful outlier that single-handedly creates the illusion of a strong correlation. It's a statistical ghost. It's a mirage in the data just manufactured by a single point. It's crazy.
You see, Anscombe created this quartet to prove one vital, powerful point. Numbers can lie. Summary statistics can be a wolf in sheep's clothing, hiding the real story. The lesson here? It's simple. You must always visualize your data. It is the only way to really see the truth.
All right, so we've learned to be skeptical of averages and to always visualize our data. But what happens when combining data doesn't just hide the truth, but actually reverses it completely? That brings us to our final and probably most counterintuitive trap.
It's called Simpson's paradox, and it's basically a statistical magic trick. You see one thing when you look at the big picture, but when you zoom in and look at the individual parts, you see something completely different, sometimes the exact opposite. It's an illusion that can lead to some seriously flawed conclusions.
So imagine you're a doctor deciding between two treatments for kidney stones. You look at the overall results from a big study. Treatment B has an 83% success rate. Treatment A is at 78%. Seems like a no-brainer, right? B is the clear winner.
The choice seems obvious. We should always use treatment B. Or should we?
Okay, prepare for your mind to be blown. When the researchers broke the data down by a hidden factor, the size of the kidney stones, the results completely flipped on their head. For small stones, treatment A is better. And for large stones, treatment A is still better. So how is this even possible?
The culprit was what's called a lurking variable, in this case, the stone size. You see, the doctors, being smart, were giving the more effective treatment, treatment A, to the most difficult cases, the patients with large stones. It's kind of like a teacher giving the hardest exam questions to the smartest students. Their overall average score might end up being lower than a class that got an easy test, but that doesn't mean they aren't the better students. The difficulty of the cases was skewing the results.
Wow. Okay, so we've seen how averages can drown us, how summary stats can totally deceive us, and how just grouping data can lead us to the exact wrong conclusion. So what's the big takeaway here? It's all about building a new mental toolkit for when you run into data out in the wild. And here it is, your critical thinking toolkit. First, always question the average. Remember that drowning statistician. Second, demand the median, especially for that skewed data we talked about. Third, never, ever trust a summary statistic alone. Demand to see the chart. And fourth, look for hidden groups. Ask if a Simpson's paradox could be at play. This toolkit, this is your secret weapon. It's your shield against spin and your sword for cutting through all the noise to find what's really going on.
This really empowers you to go beyond the headline number and just become a more informed, more critical thinker. Because the truth is rarely in that single number we're given. It's in the questions we learn to ask about it. So the next time a chart or a stat flashes across your screen, you'll know exactly what to do. And that, my friends, is a superpower.